Welcome to the Camo Monster. In this video, we are going to learn about the basic concept of design of a distillation column. First of all, the method of separation of a distillation column is the boiling point difference. We know that the property difference between the components to be separated classify an equipment. Like if we have a size difference, we can't separate it by distillation column because it is based on the relative volatility of or boiling point difference. Or for the separation based on size, we will definitely move toward a mesh sieve size separator or a membrane type separator. So it is important to understand that the property difference we have in the components that are to be separated define us or show us what type of equipment we should use for the separation of those components. Like in the distillation column, there will be one feed entry point. Actually, the distillation column consists of a vessel, a column in which there can be trays or there can be packings. The packing type distillation column is often discouraged, and the reasons of it will be discussed in a later video. So here will be the trays inside the column, and there will be a feed point. One of the design feature will be the calculation of the feed location. Like we will try to find at first plate or second plate or third plate the feed is entering, or it is entering at fourth or fifth plate. So it will also a design feature. Like we have the vapor moves upward. Vapor have natural tendency to move upward while the liquid flows downward. These arrows are pointing the downward direction through the downcomers. These are called the downcomers, and there is also a weir on the plates that will be discussed. On the above side, we have a condenser. The vapor that move upward are condensed by using the cooling water, or sometimes if we have some certain components that have very low boiling point, then we can use refrigerants in the condenser. The vapors that are condensed that can be classified on the basis of two types of condenser. Like we have a partial condenser or we have a total condenser. In the total condenser, all the vapors that enter the condenser are condensed, and there is no composition difference between the overhead product and the reflux. But in the partial condenser, there will be a few vapors and there will be a few liquid. Like we have got in the condenser 50% liquid and 50% vapor. So there will be different composition in the reflux and overhead product, because the overhead product is always liquid, whether we have vapor inside this stream or we have liquid inside the stream. Then the use of pump is discouraged if we have vapor, because pump produce cavitation. If we have vapor, pump is based on the liquid pressure difference, while the compressor is based on the vapor or air or gas pressure difference. Like in the bottom, we can also see a reboiler. In the reboiler, the bottom liquid goes and it is boiled at its boiling point. For example, if we have methane or ethane or we have water even, it is boiled at its boiling point inside the reboiler. So the vapor that forms rise up through the upcomers for the downflow and downcomers for the liquids. Or these spaces, I mean to say these spaces act as a downcomer for the liquid that is moving downside, or it acts as an upcomer for the vapors that move upside. In this, the steam or condensate is used, and the bottom products in the form of liquids are separated, while the high volatile vapors are separated. It is also based on the two types. Reboiler can be of the kettle type reboiler, or it can be a thermosiphon. The design of a thermosiphon is mostly a vertical shell with tubes inside it, most similar to the shell and tube type heat exchanger. While the kettle type reboiler is different, and there is a composition difference, so you can have bottom product and the vapor having different composition, while in thermosiphon both have the same composition. The next, we talk about the number of components. Like if we have only two components, for example, I have two components, methane and ethane, and I want to separate the lighter. You can simply say by common sense the methane will be lighter based on the boiling point difference. So for the binary components, we can use a simple McCabe-Thiele diagram or simple equilibrium diagrams that are available in the literature to separate the both components. But in the case of multi-component mixture, like we have higher amount of components, methane, ethane, propane, butane, pentane, for such components we can develop such a single equilibrium line, like for feed line, and one operating line and one equilibrium line, and we can create the stages between them, because there are number of components and there are number of relations between each of the equilibrium line and each of the operating line of every component. So there will be extremely complex shapes out there. So the design base of distillation column in multi-component system will be based on the stages calculation by using Lewis-Matheson method, and reflux ratio will be calculated using the Underwood method or Colburn minimum reflux ratio method. That will be discussed later during the design. Okay, then we should talk about the types of distillation column internals. Like what are the internals inside a column? Only trays. The trays are only the internal inside the column. So we can have a sieve tray, we can have a tunnel cap tray, we can have bubble cap tray, or we can have a structured packing tray. The most common that we use is the bubble cap type tray, and the reason is its capacity to handle different flows of vapor. Like if there is normal vapor, the bubble cap can adjust its position. It can move upward or downward. With the low vapor, it can also adjust its position. With high vapor, it can adjust its position to the maximum length of the weir. And here you can see the differences between the sieve, valve, and bubble cap tray. You can say the highest pressure drop in bubble cap, but efficiency is also highest and vapor capacity is lowest. But most of the cases, the bubble cap trays are used to handle variable vapor capacity, but during the steady state process, the sieve tray or valve tray are encouraged in most of the cases. However, the bubble cap trays have its own capacity, again telling to handle variable vapor flow rates. Now we should understand the important basic terminologies of the trays during the process of separation. Like we can say, if the liquid is moving downward in the direction and the vapor is rising upward, we can have a liquid holdup. We should have a liquid holdup on the tray. The liquid holdup helps to increase the mass transfer between the, because it increases the contact, so it increases the mass transfer rate between the liquid and rising vapor. So for example, in the case of bubble cap, the vapor particles bubbles through that liquid, and weir is actually only a slight extension of length at each plate that allows certain amount of liquid to be accumulated at that space, and this is called the active area of plate, because the downcomers are not active and there is only vapor downflow, vapor upflow or liquid downflow is happening there. So this is the active area of tray. And in certain cases where the liquid holdup is far more greater, but the vapor flow or vapor flow and pressure are analogous in this column, because the higher flow of the vapor will increase the vapor pressure here. If we have a high pressure, so the liquid will not weep or cry through the plate, you can say, because the pressure will be enough high. But the weeping can take place and it is discouraged. The weeping should be minimum in the amount. And also a froth can be formed. The froth is like different composition of the liquids are in contact and mixed. So with contact of vapor, they can form different layers. So you can see a froth on the surface of the active area of plate, and there can be entrainment where you can see the vapor bubbles on the top of that liquid layers that are formed over the wears. Like here the entrainment vapor particles are shown. These are actually the small bubbles that show the entrainment over the froth surface. Okay, this is the downcomer backup that is along the walls, and there is also an important concept to understand about the flooding. The flooding will happen when your vapor flow rate will increase far more than the amount of the liquid that is coming downward. If the vapor increases, or for other cases the liquid increases, the column will flooded. If the column gets flooded, there will be no mass transfer rate because the vapors and liquids, everything will be mixed up everywhere. We can't have enough hold up at the wear or plate, and we can't have any active area out there because everything will be so messed up. So the flooding should be discouraged, and the flooding flow depends on the flow rate of the vapor and the flow rate of liquid, so they must be maintained or kept minimum below the flooding point. The flooding point correlations or charts are available that will be discussed in the design of distillation column part. We have wear crust that shows the extension. That is enough to understand the basics of the design of a distillation column. The latter part will involve the complete design of our distillation column. So stay with us, stay blessed, and stay happy. Thank you.